Hello, my name is Sophia Edwards, and I'm currently in residence at the University of Tennessee Space Institute as part of the Aerospace and Defense undergraduate experience. Today, I will be discussing some of the benefits and obstacles associated with hypersonic systems, as well as ways that these challenges are being analyzed through ground tests to improve our understanding of high-speed aerodynamics. To understand hypersonics, let's first talk about what the Mach number is. The Mach number can be calculated by taking the ratio of velocity over the speed of sound, both at local conditions. Hypersonic speed is generally thought of as traveling faster than Mach 5 or 5 times the speed of sound. The need for speed is now more important than ever for our national security. Hypersonic technology will also be useful in making space reentry more efficient and will eventually reduce aircraft travel time significantly. Improvements in material technology needed for hypersonics can be used in other areas of science as well. Over on the top right of this slide, you'll see an image from NASA of the X-15. The X-15 was an experimental aircraft from the 1960s that reached Mach 6.7 in one of its test flights. As one of the first manned hypersonic vehicles, some of the challenges with hypersonic flight became very apparent. I put a 3D printed resin model of the X-15 in the test section of a Mach 4 as well as a Mach 7 Ludwig tube. Utilizing an optical diagnostic technique called Schlieren, you can visualize changes in density gradients present. This allows you to determine where shock waves and shockwave boundary layer interactions will occur. One of the X-15 flight tests had a dummy ramjet engine attached. The ramjet was connected to the body of a plane by a pylon that unfortunately took a lot of damage during the flight test. The actual damage done to the pylon is photographed in an image from NASA in the top left. The figure on the bottom left is a Schlieren of the shock-shock interaction that occurred. The bow shock off of the pylon and the oblique shock off the leading edge of the ramjet are traced in red for a better visualization of the interaction. The intersection of the two shocks led to a vortex sheet that created extreme temperature and pressure loads on the surface of the aircraft where the sheet impinged. It is apparent from these tests that the high concentration of heating and pressure can lead to a lot of problems during flight, including material failure. The ability to overcome this problem would drastically reduce the time it will take to make hypersonic travel a reality. In order to solve this problem, you will have to first understand the complex flow. Ground tests can be used to better analyze the phenomenon that cause the damage to the hypersonic systems before the flight tests occur. This helps determine the location and kind of thermal protection systems necessary, as well as recognizing geometric failure points in the aircraft design. Ground tests have the potential to save time and money, as well as increase the safety of pilots. A large portion of ground tests utilize the optical diagnostic techniques to better understand the flow. Let's look at some more images of the X-15 from the bottom view to discuss this further. We've already discussed Schlieren some, which utilizes the refractive index to allow a visualization of density changes in the flow. Another non-intrusive diagnostic is IR thermography, which uses an IR camera to obtain data for mapping heat flux. It does this by using a correlation between pixel intensity and temperature. The dark blue represents the lowest heat flux, and the red is the highest, as depicted in the color bar. The far right shows a zoomed in video of the engine that underwent damages in the X-15 flight. It is apparent that the nose of the ramjet and the leading edges of the wings heated up greatly over time. A lot of wind tunnel tests make use of more simple geometries than that of the X-15. This allows one to apply the data from simple configurations to multiple different vehicles. For example, a cone can represent the lower fuselage of an aircraft, and the cylindrical shock generator attached to the cone would represent a pylon. This is depicted in the orange boxes on the top left image from NASA. Below that image shows a 6-degree cone with a shock generator that was tested in the Mach 7 Ludwig tube. The surface of this cone was coated in temperature-sensitive paint, or TSP. TSP is another non-intrusive optical diagnostic that also utilizes a correlation between pixel intensity and temperature. It is beneficial for obtaining global surface temperature distributions because each pixel effectively works as its own temperature sensor. TSP is also able to obtain high temporal resolution. From these tests, you can visualize how the bow shock off the cylinder or the pylon, in the case of the X-15, heated the surface of the fuselage. The darker region from the shock generator displays the high concentration of heat. Although the intricacies of hypersonics can be daunting at times, it creates a cutting-edge field that has a place for anybody interested. Using the combination of numerical studies, ground tests, and flight tests, the problems encountered with shock boundary layer interactions, just one of many problems in hypersonic flight, can be resolved. While this presentation has mainly talked about how ground tests can be used to solve this issue, there's still much work to be done in numerical simulation, flight tests, and material research, creating many opportunities for everyone in STEM. Thank you for your attention.